In this video, we are going to derive this torsion formula. We're asked to use the fact that the torsion is the negative of the dot product of the derivative of b with respect to t dotted with n hat divided by the speed, and the fact that b hat is equal to this expression to show that the torsion must be equal to this expression. Now we want to start this by actually proving this. We know b hat in this way. It is the cross product of the unit tangent vector with the unit normal vector, but we may not actually know it in this form. So we want to derive this first, and then once we derive this, we're going to use this fact, which I believe I showed you in the videos already, this fact and this fact to come up with this fact. So I think it's helpful to start actually on this side and think of acceleration in terms of the unit tangent and the unit normal, and also to think of the velocity in terms of the unit tangent and the unit normal. So my plan is to evaluate this expression first and show that it's equal to that. So we're going to compute this, and we'll compute its magnitude. And then we'll use those two facts to show that this cross product of the velocity with the acceleration divided by its magnitude is actually equal to t hat cross n, which is our definition of b hat, or that binormal vector. Okay, so I think the easiest way to show this is to start by remembering how that unit tangent vector and unit normal vector are related to the acceleration and the velocity. So the unit tangent, we all know, is this. It comes from taking the derivative of r and dividing by the magnitude of r. Well, if we're thinking of r as a position function, this is the velocity divided by the magnitude of velocity. And the way we were writing it in the videos is this way. This is a lowercase nu, and it represents the speed. And that's a function of time. Okay, well with this, I can solve for velocity. And I have that the velocity is just the speed times the unit tangent vector. And I think that makes a lot of sense because the unit tangent vector is pointing in the direction that you're moving. And then we take that vector that's pointing in the direction of motion and we multiply by the speed, and that's going to give us velocity. And then we can also write the acceleration in terms of t hat and n hat. We spent a lot of time proving this before. Acceleration is a sub t times t hat plus a sub n times n hat, and a sub t turns out to be the derivative with respect to t of that speed function, and a sub n turns out to be the curvature times the speed function squared. And I'm not sure if I proved this in the videos, but we can prove that too. I think I will prove that too. Maybe not in this video, but in the next video. I believe we already derived this formula, that a sub n is equal to curvature times the speed squared. So we could rewrite this way. If we're thinking of speed as represented by that lowercase nu, we could write that as v prime times t hat plus kappa times that nu squared times n hat. And that's equal to our acceleration vector. So now I just want to compute the cross product of the velocity with the acceleration. So that's the cross product of speed times the unit tangent with this acceleration vector, which is just a sum of two terms. Sum of two vectors. Now, it's a fact that cross products work this way. If you have A crossed with B plus C, it turns out that that's the same as A crossed with B plus A crossed with C. This cross product distributes over addition. So this is the same as this crossed with this, plus this crossed with this. You're probably already seeing it. So I've got a t hat cross n hat, and that's looking a lot like my binormal vector. Now this guy, oops, I lost my prime somewhere. This guy is 0, because remember, this is just a scalar function of t times t hat, and another scalar function of t times t hat. So those two vectors actually point, or they're parallel to each other. I was going to say that they point in the same direction, but it's not that they necessarily point in the same direction, but they either point in the same direction or opposite directions. Since they're parallel to each other, the cross product is 0. Now over here, you've got a scalar and a scalar and a scalar. Now, the way scalars work, you can factor those out anytime you're taking a cross product. So this times this, when you take the cross product, is actually, if I factor out the scalars, I've got kappa times, I've got my nu squared here and my nu here, so that's kappa times nu cubed times t hat cross n hat. Okay, and that's our binormal vector. So that's nice. I'm trying to get the binormal vector by itself. I can take this guy and I can divide by its magnitude. Or I can take this guy and divide by this. Now, I could also just take this guy and divide by its magnitude. You might say, well, how do you know that the magnitude of this is the same as that? Well, this is a unit vector. So this tells me that the cross product of velocity with acceleration is this scalar function times this unit vector. So the magnitude of this guy is this guy. So when I take that and I solve for b hat, that's actually this vector divided by this, which is the magnitude of that vector. The magnitude of that vector is just that constant that's, or that function of t that's out front, multiplying b hat, which we know is a unit vector. Okay, so we proved that part, and now we want to use that fact and this fact to derive this formula. So my plan is to just compute this expression and show that this expression has to be equal to this. We're going to use the fact that parallel vectors have a 0 cross product a lot. So keep that in mind. And rather than using this in terms of velocity and acceleration, I'm going to write it in terms of r, so it looks a little bit more like the result we're aiming for. V is r prime, and a acceleration is r double prime. Okay, so I want to compute this negative derivative of b dotted with n hat, all divided by that scalar there. Okay, so the derivative of this, actually it might be easier, instead of using this form to use this form. Well, no, this is fine, actually. I'm going to take the derivative of this. I think I am going to do it that way. I'm going to think of this as this over that kappa times nu squared. So maybe I'll write that way. I've got a scalar function of t times this cross product. I want to compute that, and then I want to dot it with n hat. And then I want to divide the result by that. Well, in order to take this derivative, I can use a product rule that applies to scalar functions times vector functions. So we're going to say this is the first function times the derivative of the second function plus the second function times the derivative of that first function. Okay. We're going to take all of that and we're going to dot it with n in a little bit. Okay, and all of that is divided by another nu. This is just a lot of computation. Now, cross products also obey the product rule. So we're going to have negative 1 over kappa times nu squared times the derivative of this product. It's the first times the derivative of the second plus the second, or plus the derivative of the first times the second. We have to be careful about the order whenever we're applying the product rule in cross products, because we know changing the order changes things. But what we do is we do the first times the derivative of the second plus the derivative of the first times the second. And R double prime crossed with R double prime is 0, because of course those are the same vector, so they're parallel, and their cross product is 0. So we've got that there. That's this piece, and then we're doing this over here. I think I'm just going to leave that piece alone. It's just the derivative of this scalar function times this. And all of this is dotted with n hat. And then we take the result and we divide everything by nu. So I guess if we wanted to, we could do it this way. We could call this, let's take this guy and multiply by 1 over nu. And now I've got R prime crossed with R triple prime plus this 1 over nu times this scalar function of t times this cross product. And we're taking all of this and we're dotting it with n hat. Now, if I want to dot this with n hat, it would be helpful to write n hat in terms of R prime and R double prime, since since we would have a lot of cancellations, since we know how R prime, R double prime, and their cross product should be related to each other. Just having this as n hat isn't as insightful as having n hat written in terms of other functions. So let's figure out what that is. Okay, well, we can do that just by doing this little aside. Recall that the acceleration vector is a sub t times t hat plus a sub n times n hat. Well, I can take that and I can rearrange it. And remember what a sub t was. I claim it's the derivative with respect to t of the speed function. And a sub n, I believe we proved this earlier, was that curvature times the speed squared. And all of that's equal to the acceleration function. Well, if I want this in terms of R prime and R double prime, well, I can write this equation in terms of R prime and R double prime. So, and then we can solve for n hat. Well, acceleration is R double prime. And I'm going to call this nu again. And I'm just going to call that nu prime for the derivative of nu with respect to t. And t hat is R prime divided by its magnitude. So there's an extra factor of 1 over nu there. And this is equal to kappa times the speed squared, so I'll call that nu squared times n hat. So let's take this and solve for n hat. We're going to subtract this guy from both sides. And then we'll divide everything by kappa times nu squared. Or you can write it as an extra factor out front. This is 1 over kappa times nu squared times r double prime. And then you've got 1 over nu prime, and that kappa times nu squared is going to end up in the denominator here. So you're going to end up with kappa times nu cubed times r prime. And you subtract those two vectors, and that gives you n hat. So I'm going to use that here, this expression here, right here. Okay, so I've got this negative kappa over nu to the fourth, and I've got a dot product happening here. Now, dot products distribute over addition as well. So if you have a plus b dotted with, let's say, n hat, that's going to be the same as a dotted with n hat plus b dotted with n hat. So this is actually, this I'm thinking of as my first vector, that's my a, and this is my second vector, that's my b. I'm going to take that and I'm going to dot it with n hat, and then I'm going to take this and dot it with n hat as well. So let's look at our first factor. If I take that and dot it with n hat, which is this, well, that's our first part, sorry. Then I'm going to add the second part, which is this guy. And that's our coefficient function times this vector. And we're dotting that with n hat as well, which can be written in that way. Okay. And now you've got a cross product, and you have a difference of two vectors over here. But again, it's just a vector dotted with something. Whenever you have a vector dotted with something, that's going to be the same as just applying this and dotting it with this, and then adding this dotted with this. So this looks a little bit different, but we've just got a function on this side now, and then this has two terms. So it's just the same thing as this, it's just reversed, it's flipped. So we're going to have this vector dotted with this one, and we can take out that scalar, so we have a negative 1 over kappa squared, curvature squared, times our speed raised to the 6th, and then we've got r prime cross r triple prime, dotted with r double prime. So that's that piece. And then over here, you've got this times this, and you can factor out the constants. The negative times the negative will make that a positive. So we'll have v prime over kappa squared. I said v prime, that's nu prime, over kappa squared times nu to the 7th. And then this dotted with, or that cross product dotted with that. Okay, so that's that piece. I'm going to keep going. Same thing here. You've got a scalar function and a vector, and then you're dotting that vector with two terms. So you just take the dot product of this with this, and then you add the dot product of this with this. So even though this is kind of a mess, it's nothing fancy. It's just vector identities. Looks like a lot. I always think, like, if your mom sees this, she'll be really impressed that you're learning all this in school. And that's no big deal. It's just a bunch of identities. So we've got this times this. You can factor out that scalar. So this scalar times this one is going to give me a kappa. And a nu times nu squared is nu cubed. Okay, and then we're dotting with r double prime. And then we've got this whole thing dotted with this guy. And you can factor that out as well, that scalar function and the scalar function. So we're going to end up with negative nu prime over kappa times nu to the fourth from that nu cubed and that nu. And then we still have the derivative of this guy. And then we've got that cross product dotted with r prime. Okay, now this looks much more complicated than it is, because remember how cross products work. If I've got a vector, or if I have a plane that contains the vectors u and v, the cross product of u with v, well, u cross v is going to go in one direction, and v cross u is going to go in the other direction. But both of those vectors are perpendicular to the plane that contains u and v, or I guess we would typically say normal to the plane that contains u and v. So this r, well, actually this one's fine. R double prime is not necessarily in the plane that contains r prime and r triple prime, so we're going to leave that one alone. But this vector is orthogonal to r prime because it's got an r prime in it. It's like taking the cross product of u with v and then dotting it with u. Well, by design, that's going to be 0. So this is 0. And similarly, this is like u cross v dotted with v. Well, if I take the cross product of those and I dot it with a vector, that vector v that I came up with or that I used in the first place to compute that, well, they're going to meet at a 90-degree angle. So that's 0. And then over here, I've got an r prime in this cross product. So this is definitely orthogonal to r prime. So this is 0. Wow, it's looking a lot more like our torsion formula. Because this is gone, this is gone, this is gone. And the only thing we have left is this. And I claim at the beginning we started with torsion equals this. Now I've got r prime crossed with r triple prime, dotted with r double prime, and the numerator over kappa squared times nu to the 6th. And what we're trying to prove is that this is equal to this. That numerator kind of looks like that, but it's not quite the same. We're going to be able to prove that in a little bit. And this denominator is supposed to be the cross product of r prime and r double prime squared. Okay, so let's look at the cross product of r prime and r double prime squared. Remember what we did earlier when we came up with that formula for b hat? Well, we used the cross product of r prime and r double prime to get this. And then we said that the magnitude of this was kappa times v to the 3rd. So using this fact from earlier, we've got the magnitude of r prime and r double prime is just the magnitude of this vector. That's a scalar times a unit vector. So it's just going to be the scalar. Well, don't you see it? It's that in the denominator. So that's kappa times nu cubed squared. And that is that magnitude squared. Now, one thing that we can do in order to change that negative sign to a positive sign is we can switch those two in the cross product. So this is equal to this, r triple prime, crossed with r prime, dotted with r double prime. And the claim is that this is equal to this. You might say, how on earth is the cross product of r prime and r double prime dotted with r triple prime equal to this? and it actually turns out that those two are equal to each other. That's the last thing that we have to show to prove that this fact and this fact lead to this fact. So yeah, let's show that this expression in the numerator is the same as this expression in this numerator. And then we'll be done. It's just a lot of vector identities. Okay. So let's look at the cross product of r prime and r double prime. Well, if r is a vector with components x, y, and z, I'm going to have r prime in that row, r double prime in that row. And if I take the cross product, I get, cross out this row in this column, y prime, z double prime minus z prime times y double prime times I hat minus, cross out this row in this column, x prime times z double prime minus z prime times x double prime times j hat. Cross out this row in this column, x prime, y double prime minus y prime times x double prime times k hat. So I've got all of that there. I'm going to write this in component form now. And that negative times that negative makes that positive. So if I just switch the order, I get this. Oops, that should be a single prime, not a double prime. Gotta be really careful about that stuff when you're doing these derivations. Okay, so that's r prime crossed with r double prime, and I want to take the dot product of that with r triple prime. Well, r triple prime is just a vector with y or x triple prime, y triple prime, and z triple prime as its components. So if I take the dot product of this with this, all I do is I take the x component of this and the x component of this, and I add, and then I add the y component times the y component, and I add the z component times the z component, and I add. This is not the most elegant way. I'm sure that there's a much more elegant way, but this is the way I thought of. So we're going to take this and multiply by x triple prime. And then we'll take this and we'll multiply by a y triple prime. I think I'm going to start writing the letters in alphabetical order. So I have x double prime, y triple prime, z prime, and then I'll have negative x prime, y triple prime, z double prime, okay? And then over here on the last one, I've got x prime, y double prime, z triple prime, and let's see, negative x double prime, y prime, z triple prime. Is there any way I can simplify that at all? Trying to see if there are any patterns there. I mean, of course, we could factor out the x triple prime, the y triple prime, and the z triple prime. But are there any factors that cancel? I don't see any. Okay, so that's that one. And I'd like to show that this expression here is equal to the expression that we had in our numerator over here. You've got r triple prime crossed with r prime, and we're dotting that with r double prime. And there are some identities that shorten this for you. But we would have to derive those as well. And I guess we could derive them with vectors u, v, and w and do this same thing, but I'm not going to do that this time. I'm just going to do it for r double prime and r triple prime and r prime. So do the cross product. You have this times this minus this times that. Cross out that row and that column. This times this minus this times -1. So we're just going to do that times that minus that times that. Okay. And then last one, cross out this row in this column, this times this. Minus this times this. And we're taking this result and we're dotting it with our double prime, which has these components. Okay, so the dot product of this guy with this guy is the following. We've got x double prime, y triple prime, z prime. I'm taking my x component and multiplying it by my x component. And then I add the y component multiplied by the y component. So I end up with x prime, y double prime, z triple prime, minus x triple prime, y double prime, z prime. Last one, this times this. Oops, I didn't write it in the order I usually like to write it in. That's okay though. We know multiplication is commutative, so we can still check. All right, so that's this. The claim is that this and this are the same. So let's check it out. Do I have any x triple prime, y prime, z double prime terms? X triple prime, y double prime, or no, it's x triple prime, y prime, and z double prime. X triple prime, y prime, and z double prime. Oh, there it is. It's just written in the wrong order. That's why I should have put them in the same order. X triple prime, y prime, and z double prime, those are the same. So those are taken care of. Okay, then I need a negative x triple prime, y double prime, z prime. Negative x triple prime, y double prime, z prime. So that's gone. So these guys are taken care of in the first row. Now I need x double prime, y triple prime, z prime. X double prime, y triple prime, z prime is right there. X prime, y triple prime, z double prime. That's right here, and they're both negative, good. And then the last one, you've got this, x prime, y double prime, z triple prime. That's that one. And then x double prime, y prime, z triple prime. And it's negative, and that's that one. So it turns out that this expression here and this expression in our numerator are the same. So, this is equal to what we were trying to prove it was equal to. It was r prime cross r double prime dotted with r triple prime. And what's nice about this is when it's written in this way, you can remember r prime, r double prime, r triple prime. Just remember you do the cross product and then the dot product. Otherwise, it wouldn't make sense. Divided by this. And that was what we were trying to prove.